Greetings, this video is going to be for those that could not be in class the day we actually discussed COD. Sorry, this is not Call of Duty. Some of you got maybe a little excited there, but it's going to be called the coefficient of determination, which is really our R-squared value. And R is the same R that we have talked about before with correlation. So for example, if I had 12 popular candy bars, and these are all the actual calorie contents of them that I went and researched, I've got anything from an Almond Joy down to a Twix here. If a new candy bar were to hit the market, if we had like a chocolate stats bar, then what would be our best guess, just pure guessing, based on these 12 candy bars, how many calories that candy bar would have? Well, if we don't know what's in that candy bar at all, okay, we have no idea if it's got peanut butter or nougat or whatever kind of filling we could stick in this thing. You know, maybe it's just like a regular Hershey bar. Maybe it's just chocolate. Who knows? But our best guess, based on 12 other candy bars, would be, well, it may not be less than 100 gram that has the fewest amount of calories. And maybe, just maybe, it wouldn't be any greater than a Twix, which is our max at 286.1. If I were to guess, I would say it's probably going to be somewhere maybe in between 190 and 286.1. And so what would that be called if we really found out what the middle value, or if we wanted to consider all of these numbers, we would say, well, what's the mean of all these candy bars? And that would honestly be your best guess at how many calories a new stat chocolate bar would be. Okay? So I've already done all the math here for you. The mean of all of these numbers would be 248.025 calories. So 248 calories, just a little over 248, would really be our best guess if that was all the information that we currently had. Now, could we have used the median? Sure, we could have used the median, but we're just going to focus on the mean right now. Now, if I were to look at nutritional facts, and if I'm looking at calories, the next thing I would personally look at would be how much fat is in that item, especially a candy bar, right? You know there's going to be quite a bit of calories, and I want to know how much fat is going to be. It's how much fat and how much saturated fat. Now, other people may say, well, I would look at protein, or I would look at how many carbohydrates, or I would look at whatever. Personally, for me, I would look at, after calories, how much fat's in it. And usually fat is the next thing after calories on a nutrition fact label. Now, the amount of fat does play a role in the number of calories contained in a candy bar, but is it the only factor? And some of you may know this, that there are 3 things that determine the number of calories in any food item. One of them is fat. The other things, and I'll enlarge this nutrition fact label here, sometimes at the bottom of a nutrition fact label, it'll actually tell you where the calories come from. And it's based on the following 3 things: fat, carbohydrates, and protein. Okay, those are the 3 pieces of the calorie puzzle. So how much calories come from cholesterol? 0. How much calories come from sodium? 0. Vitamin A and all your minerals and vitamins, how many calories come from those things? 0. It's truly only the fat, the carbohydrates, and the protein that make up these calories. Okay, and we've got something super fatty and not healthy for us. I don't even know where I got this nutrition fact label from, but it's not good, right? Now, the other numbers that are down here, for every gram of fat, we get 9 calories. For every gram of carbohydrates, that's 4 calories. For every gram of protein, there's another 4 calories. And so really, if we did the math, you know, if we said there's 27 grams of fat here, if we multiply that number by 9, and if we took the number of carbohydrates, which is 29, and multiply that by 4, and the total number of grams of protein, which is 39, and multiply that by 4, if I were to add together these 3 quantities, it should come really close. It's usually not an exact fit here, but it should be close to the number of calories at 520. Okay, so that's how calories are calculated. So to throw this in here, carbohydrates and protein are also factors besides fat. So, do you think that you could predict the number of calories a candy bar has just based on the amount of fat it contains? And well, if we just said there were three things altogether, fat, carbohydrates, and protein, that really make up calories, just using fat, we could use it as a predictor, but it's not going to be the greatest because, well, what about the carbohydrates? What about the protein? So we would say no, but how well does the amount of fat in a candy bar predict how many calories it will have? That's what this R-squared number is going to tell us. Okay, and R-squared is essentially, it's like a grade, if you will. It's going to be a percentage. We could write it as a decimal or a proportion, but most of the time you're going to see the R-squared value as a percent, which means the lowest it'll be is 0, the highest it'll be is 100. So R-squared is the grade that our regression line gets for predicting Y values based on actual X values. To put that into perspective of this problem, R-squared is going to be the grade that our regression line will get for predicting calories based on the actual amounts of fat contained in our candy bars. Okay? So the higher the R-squared value, the better our regression line will be at predicting the number of calories from actual fat content. Okay? The lower the R-squared value, let's say we had an R-squared of 10%. Well, that's telling us that the regression line is going to be awful at predicting Y values for actual grams of fat. Okay, so the higher the better at doing really good jobs at predicting. Now, this next part is really where the R-squared value comes from, how it's calculated. And I do not expect any of you to be able to, like by a long hand here, calculate the R-squared value. We'll talk about a much easier, simpler way. I mean, the calculator even gives you the R-squared value. But even if we had just, say, the correlation value R, well, that's really just going to be squaring that to get the R-squared. But here's the idea behind R-squared. This line right here, this is our 248 that we mentioned earlier would be our best guess for how many calories a candy bar would have that would come out on the market. And so all of these points on here represent those 12 candy bars I gave you. So this one right here that has 190 calories, well, that was that, what was that, the 100 gram bar? Jump back real quick. Yeah, the 100 gram bar. And the 286 was our Twix. So if we go back and look here, 286 was our peak. This point right here is the Twix. And everything in between are all the other 10 candy bars. So you'll notice there's these pink lines. And what do these pink lines represent? Well, those pink lines represent the residuals, okay? Because the predictor line, 248, and it's always going to be 248 because it's a flat horizontal line, would be how many calories we would predict all of our candy bars to be. And so if a 100 gram bar was really 190.5, well, we would predict it to be 248, and 248 minus the 190.5, this amount is the residual. And so all of those other vertical lines there represent the residuals of all of our candy bars, using 248 as the only prediction for all of those candy bars. So this 248 represents a line of fit, but it's not the line of best fit. It doesn't reduce, it doesn't, our least squares that we had mentioned before, it doesn't make it the least possible. It doesn't minimize those squares. Now, just to remind you, where do the squares come from when we have nothing but lines in here? If we were to square the amount of air in each one of these, so basically make squares out of these, you might go, why do we want to make squares out of them? Why don't we just take all of those residuals and add them all together? Well, we mentioned before, if we were to add all the residuals, well, we have positives and we have negatives, and in the end, all the positives will cancel out all the negatives. So to bypass all that positives and negatives canceling each other out, we can square all of our residuals and make them positive, and then we can add them together. So there's this thing called the SSM. It is the sum of the squares of the mean. If I were to take all these residuals and square them, literally make them squares, and add together all of those areas, this is what the area would be, and that's the total air using purely the mean of 248 for all of those candy bars. Well, if I were to actually do the LSRL, the line of best fit, here's what the equation of that line would be. It'd be 168.8 plus 6.82 or 6.832 times x. Now again, remember, X represents the number of grams of fat, and our Y hat is our prediction for how many calories that candy bar would have for that many grams of fat. Now, if I were to also look at all of these residuals, I can already tell these residuals are a little bit smaller in value than the ones over here. And so again, if I were to square all of these residuals and add them all together, I'm going to get a smaller number, which is why it's called the least squares. These are the smallest squares cumulatively that we could get out of any regression line. All right, so if I took all of those squares and added them all together, I got this number, 7,443.9, which is quite a reduction, over 3,000, like 2,300 if we will, not 2,300, 3,200, sorry. There was a reduction of around 3,200 in the amount of air that I was off when I used the regression line versus just using the mean. So here's where the R-squared comes into play. I look at that difference for how much I got to reduce the error by using the regression line. So that difference, that 3,200 number, out of all of the error that I had in my worst case scenario, that 10,000 number, puts my R-squared value at 0.3 or 30%. So here's how I would interpret that. That 30% of the variation in calories, what I'm trying to predict, can be explained by the regression line, the least square regression line, using grams of fat, which means 70% of the variation, right? Because we had a lot of variation going on here, right? We had some residuals that we didn't really hardly have any points that were just on the regression line. All of these varied quite a bit here. So 70% of the variation cannot be explained by the regression line using fat, which means where does that other 70% come from that does explain for the amount of calories? Well, it comes from the other two things that we mentioned earlier. The grams of carbohydrates and the grams of protein. Okay, so if we were to look at the R-squared for fat, protein, and carbohydrate, together we should get something around 100% of the variation accounted for by using all three of those regression lines. But we would never really do all three regression lines at the same time. We want to use one thing to predict one other thing. Now there is something called multiple regression, where you could in fact use fat, carbohydrates, and protein to predict something. But that's not for a first level stats class. That's for a much higher level class. So our R-squared value, it is called the COD, or the coefficient of determination. R, our correlation value that we really started out the chapter with, it measured strength and direction of a linear association. And R-squared is going to measure how well our regression line does at reducing variation. All right, here is the main thing. You're going to kind of have to just build into your head. You're going to need to take a mental screenshot here of this statement. This is going to be our general R-squared statement. If I say interpret this R-squared value, you're going to say the R-squared, whatever that is, whatever it is as a percent, that percent of the variation in whatever Y is. So our Y in the candy bar problem was calories. So that percent of the variation in the number of calories is explained by, or can be explained by, the LSRL, the line of best fit, using whatever we were using for X. And what were we using for X earlier to predict calories? We were using grams of fat. Okay, so the underlying values here, the R-squared, you actually need to put the number in there. The Y needs to be in context to the problem. So we would have said calories in this case. And the X again needs to be in context. So again, we said it would be grams of fat. The last part here is I want to kind of leave this up to you guys. I'm just going to call this kind of a fake quiz, if you will. 4 questions. And this is all related to, for the most part, R-squared. Now, problem number 4 here says, after calculating the regression line of jump on year for the Chapter 3 project, this is something that I did in a previous year, and I just haven't changed the context of this. So don't go, oh crap, I didn't know we did a Chapter 3 project. Just know that when we talk about jump, we're talking about the jump distance, and whenever we talk about the year, we're talking about how many years it's been in the past. So the whole gist of this project was, could we use how far long jumpers, that jumpers in the Olympics, if they did the long jump, could we predict how far a person could jump in a future Olympic session? So we were using the years as our explanatory variable, and how far they jumped in distance as our predicted y value. Okay, so that's all you really need to know here. The main thing I want to know is, this is the r squared value, interpret it in context of this problem. All right, so try these 4 out, and then when you come to class and you see me again, just run these 4 by me real quick. I'll let you know if you got them right or you got them wrong. And that's it for this video.